Welcome back to the deep dive. I'm your host, and I'm here with our resident mycology expert. Today, I actually want to start by asking you to look down.
Straight down at the ground.
Yeah, literally just look down. Imagine you are walking across a grassy field.
Hmm.
Maybe it is a park or a cow pasture or just, the verge on the side of a country road.
Okay, I am picturing it.
You are looking at the grass, and suddenly the chaos of nature kind of just organizes itself. You see a shape. A perfect circle.
It creates this intense moment of cognitive dissonance, doesn't it?
It really does.
Because nature usually doesn't do perfect geometry. We expect jagged lines and randomness. But then you see this ring of lush, dark green grass.
Or maybe a ring of dead brown turf.
Right. Or if the timing is absolutely right, a perfect circle of white mushrooms.
The fairy ring. It is one of those things that feels like it belongs entirely in a storybook. And for centuries, that is exactly where people put it.
Oh yeah, the folklore is wild.
Folklore tells us it is where witches danced or where elves partied or even where the devil churned his butter.
The devil churning butter is a very specific image.
It is. But the reality, the actual science behind it, is arguably wilder than any of that fiction.
I would absolutely argue it is significantly stranger, because we aren't talking about magic here. We are talking about a biological marvel.
We really are.
We are dealing with massive underground networks and chemical warfare and this concept of self-DNA toxicity.
Not to mention a fungus that keeps a calendar better than I do.
Exactly.
And specifically, we are tracking down the main architect of many of these rings today. The St. George's mushroom, Calocybe gambosa.
Yes, the Spring King.
It is a mushroom that just breaks all the rules while everything else is waiting for autumn to arrive. This thing wakes up in the middle of spring and just starts terraforming the soil.
Terraforming is honestly the exact right word for it. We so often think of mushrooms as these passive little umbrellas that just pop up and then rot away a few days later.
Right, like they're just fragile little things.
But today's deep dive is going to completely challenge that idea. We are looking at a massive, centuries-old organism.
Centuries old.
Oh, yeah. An organism that actively manipulates the physics of water in the soil. It drugs the plants above it with hormones, and it fights off bacteria by literally jamming their communication signals.
To get to the bottom of all this, we have pulled together a really fascinating stack of sources for you today.
A very diverse stack.
Very. We have a 2022 study out of Serbia that didn't just analyze the chemistry of this mushroom. They actually baked it into oatmeal cookies.
Which is a sentence I truly never thought I would see in a peer-reviewed scientific journal.
I know, right? Baking cookies for science. But they did it to prove a point about functional food.
And the results were surprisingly relevant.
We also have a massive comprehensive review from 2025 on the ecology and history of fungal fairy rings, or FFRs as they call them in the literature.
That paper really gets into the mechanics of how these rings actually move through the earth.
It does. Plus, we have the essential foraging guides, because as we will learn, misidentifying this particular mushroom can have some pretty severe consequences.
Absolutely. There is a deadly lookalike involved in this story.
So we will cover the danger in the cookies. But our overall mission today is to really understand the Holobiont.
The Holobiont, yes.
We want to understand the fairy ring, not just as a fungus, but as an entire moving ecosystem. So let us start with our protagonist, the St. George's mushroom.
Calocybe gambosa.
The common name alone feels very specific. Why St. George?
Well, it is all about the calendar. In the UK and much of Europe, St. George's Day falls on April 23rd.
Right.
Now, if you are a forager, you know that spring is usually the time for green things. You are looking for wild garlic or fresh nettles.
Mushrooms are typically an autumn affair, linked to rotting leaves and damp, cooling earth in October.
Exactly. October is fungi season for most people, but Calocybe gambosa is a rule breaker. It is definitively a spring mushroom.
So it pops up in April.
It tends to fruit right around that late April mark, often specifically on or within a few days of St. George's Day.
It is weirdly precise. I mean, how does a fungus know what date it is? It doesn't have a calendar down there.
Well, it doesn't have a calendar, no, but it does have a very specific set of environmental triggers that it responds to.
Okay, like what?
It is a saprophyte, which means it feeds on dead organic matter in the soil. And the working theory is that the late frosts of winter actually help break down that organic material.
So the freezing temperatures are doing some of the heavy lifting.
Yes, exactly. The frost literally cracks open the cell walls of the dead grass and leaves from the previous year.
I see. So the frost does the prep work?
It releases all those trapped nutrients, so when the temperature finally starts to rise in April, the mycelium, which is the underground root-like structure of the fungus, is just sitting in this massive buffet of readily available food.
And it just gorges itself.
It has this huge surge of energy, so it can produce fruit bodies long before the other autumn mushrooms are even waking up.
Let us unpack the scientific name for a second. Calocybe gambosa. Because you always say the Latin holds the secrets.
It usually does, though in this case it is a mix. Calocybe is actually a mashup of ancient Greek.
Okay, let's hear the Greek.
Kalos means pretty, and kubos means head.
Pretty head.
Literally pretty head, yes.
That is surprisingly cute for a scientific name. Usually they are so clinical.
It is cute, but it fits perfectly. It has a very smooth, clean, white to cream colored cap. It looks very tidy.
And then there's the second part.
Right, the species name, gambosa. That part is Latin, and it is a bit less flattering than pretty head.
What does it mean?
It means club-footed.
Club-footed. Wow, they really give it the take it away with this name.
Yeah.
Pretty head, club-foot.
They do, but the club-footed part refers to the stem. If you dig one up, you will see that the base of the stem is often very bulbous. It is thick and swollen.
Like it's wearing a heavy boot.
Exactly. It looks sturdy like a club. It is not one of those delicate, spindly little mushrooms you see in the grass. It is a chunky, solid thing.
I love how these common names travel, too. In the UK, it is St. George's. But in the sources I was reading, that in Germany, they call it mypills.
Which translates directly to the May mushroom.
And in Tuscany, down in Italy, it's known as Pickling or Fungo marzellino.
Marzellino, coming from the Italian word marzo, which means March.
March. That is a full month earlier than St. George's Day.
Well, you have to think about the regional climate. Tuscany warms up significantly earlier in the year than, say, the Yorkshire Dales in England.
Oh, that makes total sense.
The mushroom is just responding to the soil temperature. In the warmer climate of Italy, that temperature trigger happens all the way back in March.
And then I saw in the Basque Country, they kind of split the difference. They eat it on the Feast of St. Prudence, which is April 28th.
It is a mushroom that really seems to anchor local communities to the turning of the seasons.
Yeah, I was reading about these huge Sagra festivals in Italy. It is not just about eating a mushroom, right? It is this whole celebration that spring has finally arrived.
It is highly, highly prized in Southern Europe. In the UK, it is often overlooked by casual walkers, but in places like Italy and Spain, it is a true culinary icon. It marks the end of winter just as much as seeing the first swallows arrive.
Okay, let us get practical for our listeners. Because if you are walking through a field in late April, how do you know you're actually looking at a St. George's mushroom and not just some random white mushroom?
That is the big question.
Because honestly, white mushroom in a field sounds like the description of about 50 different species.
It really does. And some of those other species are incredibly dangerous. So we need to look closer at the specific identification markers.
Walk us through it. Let's start from the top.
First, you look at the cap. It should be about 5 to 15 centimeters across.
So fairly substantial.
Yes, a good size. It starts out convex, like a dome, but it flattens out as it ages. The texture is key here, though. It is often described in field guides as feeling like white kid glove leather.
So soft, smooth, dry.
Very smooth, dry, and soft. It is never slimy or sticky. And then you need to look at the rim of the cap. The margin is often enrolled.
Enrolled meaning what exactly?
It means the very edge of the cap curls and tucks underneath itself towards the stem, especially when the mushroom is young. It makes the whole thing look a bit like a little round bun.
Okay, cap check. Smooth leather enrolled edge. Now flip it over. What about the gills?
The gills are white to a pale cream color, and they are very, very crowded together. But here is the crucial identification feature, the one that makes experienced foragers actually get out their hand lenses.
All right, what is the secret feature?
The gills are sinuate.
Sinuate. That is a word that sounds like a snake slithering. What does that mean in mycology?
It is a term that describes exactly how the gill attaches to the main stem.
Okay.
Imagine you are running your finger along the top edge of a single gill, moving from the outside edge of the cap inwards towards the stem.
Tracking your finger inward, yeah.
Just before your finger hits the stem, the gill suddenly dips down.
Like a little valley.
Exactly, like a little valley.
Hmm.
It dips down and then hooks back up to finally attach to the stem. It basically creates a tiny little gutter or a moat all the way around the top of the stalk.
Oh.
It is often called a tooth-like attachment. The gill doesn't just run straight flush into the stem, and it certainly doesn't run down the stem like a funnel.
That seems like such a tiny, obscure detail to look for.
It is a tiny detail, but in the world of foraging for white mushrooms, those tiny details are what save your liver. That sinuate attachment is a very strong primary indicator that you have Calocybe gambosa.
Okay, and then there's the stem itself. You already mentioned the club foot.
Right, the stem is thick and stout, usually 2 to 4 centimeters wide, and importantly, there is no ring.
No ring around the middle.
Correct, no little skirt hanging off the middle of the stem, and absolutely no vulva.
Remind us what a vulva is.
The vulva is that sac-like cup structure at the very base of the stem that you see on highly toxic things like the death cap.
Yeah.
St. George's doesn't have that. It is just a clean, thick, fleshy stem.
But I think the most famous identifier for this particular mushroom isn't visual at all. It is the smell.
Yes. The sensory experience of a fresh St. George's is polarizing, to say the least.
I have heard it described as mealy.
That is the standard polite field guide term.
Huh.
Farinaceous is the technical word. It means it smells strongly like wet flour or raw pancake batter.
Okay, that sounds pretty innocuous. I like pancakes.
It is a very distinct, heavy, yeasty smell. But, people's noses process aromatics differently. Some people swear up and down that it smells exactly like fresh sliced cucumber.
Really?
Cucumber.
Yeah, or even watermelon rind.
And then there are the descriptions in the much older Victorian literature.
Which can be quite graphic, yes.
Yeah.
Some of those older naturalists describe the scent as spermatic.
Right. We don't need to dive too deep into the mechanics of that specific comparison. But the main point is the smell is strong.
That is the crucial takeaway here. If you pick a white mushroom in the spring and it smells like absolutely nothing or just faintly of standard wet earth, you need to be very careful.
Because St. George's announces itself.
It has a punchy, flowery aroma. If that specific smell is missing, you should probably just walk away.
Okay, we have the look and we have the smell. Now, where are we actually standing when we find this? You mentioned grasslands earlier. It really loves open spaces. Pastures roadside, verges the edges of woodlands, and it has a very particular affinity for limestone or chalky soils.
So if you are listening to us from somewhere like the South Downs in the UK, you are basically in prime St. George's territory.
Absolutely. The calcium in the soil there seems to be a major factor.
And the growth pattern brings us all the way back to the hook at the start of the show, the ring.
Yes. You will very rarely find just one lonely St. George's mushroom. They almost always appear in large troops or these perfect geometric rings.
And the site fidelity is amazing from what I read.
Oh, it is incredible. Because the actual organism underground doesn't pack up and move. Well, it moves slowly outwards, as we will discuss, but it stays anchored in the exact same general area.
So if you find a spot, it's yours forever.
Exactly. Seasoned foragers will have their secret St. George's spots. They walk to the exact same GPS coordinate every single April 23rd, and the mushrooms will reliably be there waiting for them.
I read this staggering fact about the rings on the South Downs. Some of them are estimated to be several hundred years old. That honestly blows my mind.
It is hard to wrap your head around.
We are talking about a living organism that was already there, growing in that dirt when Shakespeare was writing plays, and it is still there, producing mushrooms in the exact same field today.
It completely changes your perspective, doesn't it? We see a mushroom and our brains immediately think ephemeral or fleeting, but the fungal colony itself is practically geologic in its lifespan.
It really is. Now, before we get completely lost in the romance of ancient fairy rings, we do have to do the safety briefing, because there is a villain in this story, the Deadly Fibercap.
Inosperma erubescens? Even the Latin name sounds like a severe warning.
It really does sound sinister. And the problem is this villain likes the exact same places, right?
Unfortunately, yes. It can grow in very similar habitats, woodland edges, parks with older trees. And while it typically appears a little bit later in the season, usually in May or June, we have to remember the climate is changing.
Right, the seasons are blurring together.
Exactly. You can absolutely find them fruiting at the exact same time, overlapping in late spring.
So let us role play this. Imagine I am out walking. I am holding a white mushroom. I think it is St. George's. How do I make absolutely sure I am not holding a Deadly Fibercap?
The first thing is to look at that species name, erubescens. In Latin, that means reddening or blushing.
Blushing.
Yes. If you split the cap of a deadly fiber cap, or if you just bruise the flesh with your thumb, it will slowly turn a bright red or pinkish color.
Like it is bleeding.
A bit like that, yes. The chemical compounds oxidize and turn pink. St. George's mushroom, on the other hand, is incredibly steadfast. It stays white.
No matter what you do to it.
You can bruise it, cut it, squash it. The flesh remains solidly white or cream. It never, ever blushes red. That is your first definitive field test.
That seems easy enough to check. What else should we look for?
The texture of the cap. Remember we said St. George's is smooth like kid glove leather?
Yes, nice and smooth.
Well, the Deadly Fibercap, as the common name literally tells you, has a fibrous cap. It looks silky but streaky, and as it ages, it often splits radially from the center outward to the edge.
So it looks kind of messy and torn.
It looks very messy compared to the neat, tidy bun of a St. George's.
And what about the smell?
The Fibercap absolutely does not smell like flour or cucumber. It has a very faint, sometimes vaguely fruity, sometimes sharply chemical smell. It completely lacks that heavy yeasty punch.
So what actually happens if you get it wrong? I mean, we throw the word deadly around, but are we talking terrible upset stomach deadly or call your family to say goodbye deadly?
We are talking about severe muscarine poisoning. It is very serious.
What does muscarine do?
It actively attacks your parasympathetic nervous system. The symptoms are awful. Profuse, uncontrolled sweating, salivation, tears, pouring down your face, blurred vision, difficulty breathing, and drastically low blood pressure.
That sounds horrific.
It can ultimately lead to cardiac failure or respiratory failure if untreated. It is absolutely not a mistake you want to casually make.
Okay, message loudly received. If it turns pink, you throw it away. If the cap is split and fibrous, throw it away. If it doesn't smell like a bakery, throw it away.
Good rules to live by. And there's actually one other safety tip that isn't about misidentifying the mushroom itself, but rather where the mushroom happens to be growing.
You mentioned roadside verges earlier?
Yes, and this is a big issue. I see people picking things on the side of the highway all the time.
Yeah, I always see cars pulled over and people wandering in the ditch.
Don't do it. Fungi are incredible bioaccumulators. They act like giant underground sponges for heavy metals and industrial pollutants.
Oh, I didn't even think about that.
If you pick a mushroom growing 5 feet from a busy road, that organism has been actively absorbing lead, cadmium, and exhaust particulates from the soil and the rain for weeks.
So that pristine, beautiful white mushroom is actually just a toxic cocktail of car exhaust.
It is a little pollution bomb waiting to be eaten. Always stick to the open fields and the deep woods, far away from heavy traffic.
Okay, we have safely foraged. We bypassed the busy road. We avoided the blushing fiber caps. And we have a basket full of clean Calocybe gambosa. Now let us finally take this bounty to the lab. I want to talk about that 2022 Serbian study.
Ah, the Ecology study.
Yes, because this wasn't just your standard boring nutritional breakdown. They got incredibly creative with their methodology.
He really did. They wanted to see if St. George's could be classified and utilized as a functional food.
Functional food meaning what exactly? A food that does more than just stop your stomach from rumbling.
Precisely. A functional food provides some sort of measurable health benefit beyond just basic caloric nutrition. But before they baked anything, they had to analyze the raw mushroom itself to see what they were working with.
What does the nutritional stat sheet look like for this thing?
Well, it is a very carb-heavy mushroom. It comes in at about 72% carbohydrates by dry weight.
Wow, that is a lot of carbs.
It is, but the protein content is where it gets interesting. In the specific samples gathered for the Serbian study, it was about 16% protein.
Which is decent for a mushroom.
But the researchers noted that other studies looking at samples from Croatia found mushrooms with up to 36% protein.
36%. That is a massive variance. How can the same species vary that wildly?
It just highlights how mushrooms are a direct product of their immediate environment. If the local soil is incredibly rich in nitrogen, the resulting mushroom will be significantly richer in protein.
So it is literally you are what you eat, but for fungi.
Exactly. It shows how responsive the Holobiont is to its local geology.
What about the fat content? I assume it is pretty low.
Very low. Only about 1.5% fat. But it isn't the amount of fat that is interesting, it is the specific quality of that fat.
What do they find?
They identified 24 different distinct fatty acids in the mushroom, but one of them absolutely dominated the profile. Linoleic acid made up a staggering 75% of the total fat content.
Linoleic acid.
Yeah.
That is an essential fatty acid for humans, right?
Mm-hmm.
We need it, but our bodies can't make it.
That is true, yes. But it is also functionally crucial for the mushroom itself. Linoleic acid serves as the direct chemical precursor to a very important compound called 1-octanthreol.
1-octanthreol. That sounds like an industrial solvent you would buy at a hardware store.
It sounds like it, but you actually know it intimately. It is known informally as the mushroom alcohol.
The mushroom alcohol.
It is this specific, volatile, organic compound that hits the olfactory receptors in your nose and instantly tells your brain, this is a mushroom.
Oh, wow.
That deep, savory, earthy, aromatic profile comes directly from the breakdown of linoleic acid.
So the high-fat content isn't just nutrition. It is literally creating the flavor profile.
Precisely. Which brings us finally to the cookies.
The cookies. I love the mental image of these serious scientists in their crisp, white lab coats mixing up oatmeal cookie dough in a sterile lab.
It is genuinely great practical science. They took a completely standard oatmeal cookie recipe, and they replaced a specific portion of the normal wheat flour with dehydrated Calocybe gambosa flakes.
So they made a control batch of regular cookies and then a stunt batch of mushroom cookies.
Exactly. And then they put both batches in front of a trained sensory evaluation panel.
These are the people whose literal job is to blindly taste things and rate them on aroma, appearance, texture, and taste.
Yes, very rigorous testing.
I'm guessing the mushroom cookies tasted pretty weird. I mean, mushroom oatmeal just sounds wrong.
That is exactly what you would expect. But the data was shocking. The mushroom-enriched cookies actually scored higher across the board than the regular control cookies.
Wait, people objectively preferred the taste of the mushroom cookie.
They did. They scored them higher on aroma, they scored better on appearance, and even consistency. The tasters specifically noted that they preferred the deeper, more complex depth of flavor.
Was that because of that linoleic acid breakdown you mentioned?
It is highly likely, yes. It seems it added this underlying savory umami depth that perfectly balanced out the cloying sweetness of the standard cookie recipe.
That is fascinating.
It really suggests that St. George's isn't just destined to be a soup ingredient. It could legitimately be used at scale to fortify commercial baked goods. It adds protein and fiber while actually making the product taste better.
Okay, so that proves the food part of functional food. But the study went much deeper into the functional medical side, too. They looked at the mushroom's antibacterial properties.
This is where the story shifts dramatically from tasty snack to biological weapon.
I love a good biological weapon tangent. They tested the mushroom extract against some heavy hitters, right? Like Staphylococcus aureus and E. coli.
They did. And the initial results against those common pathogens were honestly just moderate.
Oh. So it isn't a miracle cure.
No, the mushroom extract killed some of the bacteria, but it wasn't a broad-spectrum super killer. It certainly wasn't the next penicillin.
Okay, that's
Just
a slight.
Because then the researchers decided to test the extract for something else, something called anti-quorum sensing activity.
Quorum sensing. Okay, we really need to break this concept down slowly, because quorum sensing sounds more like a corporate middle management strategy than microbiology.
It is actually surprisingly similar to a corporate strategy. Imagine harmful bacteria are like an invading army.
Okay.
If one single solitary bacterium enters your body and attacks a cell, your immune system spots it and squashes it instantly. It is basically suicide for the bacterium.
So going in solo doesn't work.
Right. So over millions of years, bacteria have evolved a much better strategy. They wait.
They just lie in wait. Where?
They float around in your system, slowly multiplying but keeping a very low profile, not attacking. However, while they wait, they are constantly releasing these tiny little chemical signal molecules into their environment.
Like sending out a little radio ping.
Exactly like a radio ping, saying, I'm here. And crucially, they also have specific receptors on their cell walls to listen for the pings of other bacteria of the same species.
Oh, I see where this is going.
When the local concentration of those chemical signal molecules reaches a specific critical threshold of quorum, every single bacterium suddenly knows, okay, there are finally enough of us to win this fight.
So the radio chatter gets loud enough, and the microscopic commander yells, go.
Yes. And they all turn on their virulence genes simultaneously. They start releasing destructive toxins, they build impenetrable protective biofilms, and they launch a coordinated, massive assault all at once.
That is terrifyingly smart for a single-celled organism without a brain.
It is an incredible evolutionary mechanism. Now enter the St. George's mushroom extract.
What did it do?
The researchers discovered that the extract didn't necessarily kill the bacteria outright. Instead, it completely jammed the radio frequency.
It cut the communication lines.
Exactly. It actively inhibited the quorum sensing mechanisms. They tested this specifically on Pseudomonas aeruginosa.
Which is a very nasty pathogen.
Very nasty and notoriously hard to treat in hospitals. The researchers found that at sublethal doses, meaning a dose not nearly strong enough to actually kill the bacteria, the mushroom extract still completely stopped them from producing piocyanin.
What is piocyanin?
It is a key blue-green toxin that the bacteria release to damage human tissue. The mushroom just switched off the command to make it.
So the bacterial army is sitting there, fully armed, but they just never get the order to attack.
Correct. They just sit there benignly. And the mushroom extract did something else too. It actively stopped their twitching motility.
Twitching motility? That sounds deeply uncomfortable.
It is how they move. Pseudomonas has these tiny little grappling hooks on its surface called Mealy. They throw them out attached to a surface and drag themselves forward.
Like microscopic mountain climbers.
Exactly. It is how they physically spread across tissues and form massive infections. The Calocybe gambosa extract completely paralyzed these hooks.
It grounded the fleet.
It grounded the fleet and it jammed all their radios. And this is a huge deal, medically speaking, because one of the biggest cascading crises in modern medicine is antibiotic resistance.
Right, because when we use standard antibiotics, we kill off the weak bacteria, but the strong survivors mutate and evolve to be immune.
Exactly. But if you don't actually kill the bacteria, if you just temporarily silence their radios and stop them from organizing, there is drastically less evolutionary pressure for them to develop resistance in the first place.
So the mushroom is effectively fighting a pacifist war against pathogens.
Yeah.
It isn't slaughtering its enemies, it is just chemically confusing them into complete submission.
It is achieving diplomatic immunity through extremely advanced chemistry. And the working theory is that if we consume this mushroom regularly, we might be imparting a mild version of that exact defensive benefit to our own gut microbiome.
That is absolutely incredible. I'm truly never going to look at an oatmeal cookie the same way ever again.
Nor should you.
Okay, let us zoom out a bit. We have looked really closely at the chemistry happening inside the mushroom. Now, I want to look at the chemistry happening outside the mushroom. I want to talk about the physical ring.
A massive structure itself, yes.
This brings us to that massive 2025 ecological review on fungal fairy rings. Historically, before we had any real science, how did people try to explain these perfect circles popping up in their fields overnight?
Well, before we had microscopes and soil assays, we had to rely on pure imagination. We already mentioned the standard witches and elves.
Right.
In France, the rings were historically called ronds de sorcières, witches' circles. In Germany, they were known as hexen rings.
It is always witches.
Always. But even the early scientists, the Victorian naturalists attempting to study this logically, they had some pretty wild theories too.
Oh, I bet. What did they think?
They knew it wasn't magic, obviously, but they couldn't see the microscopic fungus underground, so they looked for physical explanations. One leading theory was that the rings were created by subterranean moles running in continuous circles just below the surface.
Moles. Why on earth would a mole run in a perfect 50-foot circle?
Some elaborate mating ritual, perhaps? Or confusion? The literature is fuzzy on the why.
That is hilarious. What else did they guess?
Another very popular theory was lightning. They hypothesized that a lightning bolt would strike the ground and the intense electricity would radiate outward in a perfect circle, selectively burning the grass roots.
But the rings get bigger every single year. Lightning strikes don't just slowly grow outward over decades.
No, they do not. And that is exactly why that logic fell apart pretty quickly upon actual observation. The real scientific breakthrough didn't happen until 1883.
Where was this?
At the Rothamsted Research Station in England, which is actually the oldest continuous agricultural research station in the entire world. 3 scientists there, Laws, Gilbert, and Warrington, finally decided to just dig a deep trench straight through a ring.
And what did they find in the dirt?
They found thick mats of white threads, the fungal mycelium. And more importantly, through early chemistry, they proved that exactly where the mycelium was present, the nitrogen levels in the soil were radically different from the rest of the field.
They linked the visible biology to the invisible soil chemistry?
Exactly. They proved it was a living, growing process.
So explain the actual engine of the ring to us. Why does it inherently form a circle? Why doesn't it just grow into a big square or a giant messy blob?
It is a matter of radial physics. Imagine a single microscopic spore lands in a fresh green field. The conditions are right, so it germinates.
Right.
It starts sending out hyphae, those little microscopic threads in all directions, equally searching for food in the soil.
So it starts as just a tiny dot.
Right, and as it grows equally in all directions, it becomes a solid, flat disc of fungus underground. It is ravenously eating all the decaying organic matter in the soil as it expands.
But eventually.
Eventually, the very center of that flat disc completely runs out of food. The soil there is depleted.
It literally eats itself out of house and home.
Yeah. Exactly. So the fungus is biologically forced to keep moving outward at the edges to find fresh, untouched food. The older mycelium in the dead center slowly starves and dies off.
Leaving an empty middle.
Yes. So the solid disc hollows out and becomes an expanding ring. That is known as the classic nutrient depletion theory.
That makes perfect logical sense. It is just a hungry organism continuously searching for new resources.
It makes sense, yes. But it turns out it is an incomplete picture. Recent modern research points to something much darker and more complex driving the expansion.
Darker than starvation.
Yes, a mechanism called the self-DNA theory, or autotoxicity.
Autotoxicity, meaning self-poisoning.
Exactly that. As the older mycelium in the center of the ring eventually dies and starts to decompose, it naturally releases all its own DNA and cellular waste products back into the soil.
Okay.
It turns out that unnaturally high concentrations of that specific fragmented self-DNA are highly toxic to the living organism itself.
Wait, so it literally poisons the ground behind it as it moves.
It actively salts the earth, but exclusively for itself. Other normal plants can grow there just fine. Entirely different species of fungi can move in and grow there. But Calocybe gambosa can never grow in that specific patch of dirt ever again.
Wow.
It creates this permanent biological ghost zone of its own dead DNA.
So it is not just eagerly moving outward toward fresh food. It is literally fleeing in terror from its own toxic past.
That is a very poetic and highly accurate way to put it. It is biologically forced to expand outward because it has purposefully made the center utterly uninhabitable for its own cells. This permanent toxicity ensures the ring keeps moving continuously outward and never ever turns back in on itself.
That is incredible. And this ghost zone mechanic explains a weird geographical phenomenon too, right? Why on steep hillsides like the South Downs, you often don't see full unbroken circles. You just see these weird disconnected arcs of mushrooms.
Exactly right. Gravity comes into play and messes with the chemistry. If a fairy ring is growing on a steep slope, the heavy spring rain washes all those accumulating toxic self-DNA compounds downhill.
Flowing right through the soil.
Yes. So the bottom downhill edge of the fairy ring constantly gets bathed in a concentrated wash of toxins flowing down from the top uphill edge.
So the bottom edge gets poisoned and dies.
Exactly. The bottom of the ring essentially kills itself by drowning in its own runoff, while the top edge and the sides are perfectly fine and keep happily expanding outward and uphill.
Resulting in a horseshoe shape.
You get these rotors or arcs slowly moving their way up the side of a hill or sliding sideways along the contour, but they can never grow downwards.
It is so amazing that simple gravity can so drastically shape the final biological structure.
It is all interconnected.
Now let us talk about the visual impact this underground engine has on the grass up above. Because the review paper spends a lot of time classifying different types of rings based on the vegetation damage.
Yes, the botanical impact. They classify them by type. Type 1 is the one everyone notices and takes pictures of. It is the classic fairy ring.
What does a type 1 look like?
You have two starkly distinct visual zones in the grass. You have a dead zone where the grass is brown, withered, and actively dying. And right next to it, you have a lush zone where the grass is super green, incredibly tall, and practically vibrating with health.
The dead zone and the lush zone. It genuinely sounds like the setting for a cheap sci-fi movie. Let us look at the dead zone first. Why does the grass die? Is the fungus attacking the plant roots like a parasite?
That was the assumption for a very long time. Farmers assumed the fungus was pathogenic and was actively eating their pasture grass. But it is not biology killing the grass. It is actually a physics problem.
Physics.
It is a phenomenon called hydrophobicity.
Hydrophobia, a fear of water.
Right. The fungal mycelium grows so incredibly dense under the soil that it forms a physical mat. And to protect this mat from waterlogging, the fungus secretes these specialized proteins called hydrophobins.
Hydrophobins, what do they do to the dirt?
They coat every single individual microscopic soil particle in the area, and they make the soil completely aggressively water repellent.
Think of a high-end Gore-Tex rain jacket or like a newly waxed car hood. Water hits it and just instantly beads up and rolls off.
Exactly. So the soil literally becomes completely waterproof.
That is wild.
You can have a massive torrential multi-day rainstorm, and all that water will just sit uselessly on the surface in puddles or run completely off down the hill. If you dig 2 inches down, exactly where the grass roots are desperately trying to drink the soil is bone-dry dust.
So the grass isn't being attacked or poisoned by the fungus at all. It is literally just dying of severe thirst.
It is dying of extreme drought while standing in the middle of a rainstorm. The fungus intentionally creates a localized microdesert just to rigidly manage its own ideal environment.
Why does it want a desert?
Perhaps to keep competing soil bacteria away, or just to maintain the absolute perfect internal humidity for its own cellular functions.
That is just ruthlessly efficient.
Nature very often is ruthless. But then right next to this manufactured desert, you have the lush zone. The grass there is suddenly growing twice as fast as the rest of the field, and it is a deep, dark emerald green.
What is happening there? Is that the fungus suddenly feeling guilty and saying sorry about the drought here is a parting gift.
In a weird way, sort of. This is known as the fertilization effect. As the massive fungal network continuously degrades the complex organic matter in the soil, and crucially, as the older fungal mycelium itself dies and rots, it releases a massive concentrated flush of nitrogen.
Ah, nitrogen, the holy grail of plant growth.
Yes. It releases it primarily as ammonium. Then the local soil bacteria sweep in and convert that ammonium into nitrates.
Which is basically high-grade premium fertilizer.
Exactly. It acts as a massive nitrogen bomb for the grassroots right at the expanding edge of the ring. But the review paper highlights something even more advanced happening in that lush zone, something called fairy chemicals.
Fairy chemicals. I am going to safely assume that is not the rigorous technical term used by the chemists.
No, it is the slightly sensationalized term the media grabbed onto. The actual chemical names are 2-azahypoxanthine, which we abbreviate to AHX, and imidazole 4-carboxamide, or ICA.
Let us definitely just stick to calling it AHX for the sake of our sanity. What does AHX actually do to the grass?
Well, it was initially discovered by researchers studying a completely different fairy ring mushroom called Lepista sordida, but it is now believed to be a widespread mechanism across many ring-forming species.
Okay, but what is the mechanism?
AHX actively functions as a potent plant hormone. It essentially drugs the grass.
It actively tells the grass to grow faster.
Yes. It forcibly stimulates rapid root expansion and aggressive shoot growth. It also artificially increases the chlorophyll content in the grass blades, making them much greener.
So the fungus isn't just passively dumping leftover fertilizer in the dirt. It is intentionally chemically signaling the plants to go into massive overdrive.
Yes.
But why would it expend the energy to do that? What is in it for the fungus to help the grass grow so huge?
That is the million-dollar ecological question. It is likely a symbiotic trade-off. By chemically forcing the grass to grow huge, the grass roots produce significantly more exudates, basically liquid sugars, that leak into the soil.
And the fungus loves sugar.
Exactly. The fungus happily absorbs those extra sugars. Or alternatively, it could be much simpler. Taller, thicker grass physically creates much more shade on the ground and traps morning dew, locking in the perfect high humidity that the mushroom needs to fruit successfully.
So it is essentially farming the grass for shade and sugar.
It truly is a master ecosystem engineer. It kills the grass in one spot to rigidly control the water supply, and it supercharges the grass in another spot to control the nutrients and the microclimate.
And it is controlling the bacteria, too, as we learned earlier.
Yes, absolutely.
Yeah.
The ring completely radically alters the local soil microbiome as it passes through. It simplifies the whole bacterial community.
How so?
It actively encourages specific types of helpful bacteria to follow it, ones that maybe help it break down tough soil components or clean up its own toxic waste, and it actively suppresses or silences others.
Using that radio jamming technique.
Exactly. And the paper even mentions mycoparasitism. Certain predatory bacteria like Burkholderia and even other smaller fungi like Trichoderma actually physically stalk the fairy ring.
They hunt the mushroom.
They follow right behind the expanding edge, feeding off the massive fungal mass or utilizing the uniquely altered detoxified soil left in its wake.
So when we stand in a field and look down at a fairy ring, we aren't just looking at a single, simple fungus popping out of the dirt. We are looking at an incredibly complex biological machine.
We are looking at a holobiont. That is the crucial term the paper insists we use to understand this.
Can you rigorously define holobiont for us one more time to tie this all together?
A holobiont means you have to view the entire interacting unit as the fundamental organism. The organism isn't just the white mushroom cap.
Right.
The organism is the physical fungus, plus the specific army of bacteria it deliberately recruits, plus the chemically altered waterproof soil, plus the hormonally manipulated plants above it. They are all intrinsically linked and moving slowly through the landscape together as a single functional superunit.
It is like a massive biological spaceship slowly moving through the topsoil of the Earth.
Exactly. A subterranean spaceship that, in some verified cases, has been continuously flying its route for 700 or even 2,000 years.
That is just staggering. Well, that brings us back to the practical human side of things. We have sufficiently admired the spaceship. We have successfully identified the captain, which is the St. George's.
We have safely avoided the deadly alien fibercaps.
Exactly. Now, after all this deep science, we want to actually eat the thing.
A final culinary payoff.
Is it honestly worth all the effort to hunt down and identify?
Ask anyone in Italy, absolutely yes. St. George's is firmly considered a Tier 1 premium edible mushroom for many people, but you have to treat it with a little respect in the kitchen.
So how do we prepare it? Can you just eat it completely raw in a salad?
Technically speaking, yes. It is one of the very few wild mushrooms that is generally considered safe to consume raw without causing immediate gastric distress.
Okay, but
However, remember that heavy mealy farinaceous smell we spent so much time discussing, that intense raw wet dough flavor.
oh, right. I'm guessing that translates directly to the taste if you don't cook it.
It does, and it can be extremely overpowering and honestly quite unpleasant for most palates.
Yeah.
So the universal recommendation from chefs and foragers is almost always to cook it thoroughly.
What does the heat actually do to it?
Cooking physically drives off those specific volatile raw dough compounds and completely transforms the flavor profile.
What does it transform into?
It becomes incredibly nutty, deeply savory, and very complex. And the physical texture is key here, too. Because it is a thick, club-footed, very sturdy, dense mushroom, it doesn't just instantly dissolve into a pathetic puddle of slime when you put it in a hot pan like, say, an ink cap would.
It holds its shape.
It stays very firm. It retains a really satisfying, meaty bite to it, even after long cooking.
So what is the ideal preparation? Just throw it in a hot sauté pan.
Butter. Sauté it in a generous amount of good butter. Just butter, maybe a tiny pinch of flaky sea salt, and some fresh cracked black pepper. Do not overcomplicate the dish with heavy garlic or strong herbs.
Let the mushroom be the star.
Let the mushroom speak for itself. Because it inherently has such a strong, robust flavor, it can actually stand up to very distinct, heavy culinary partners without getting lost.
What kind of partners?
It pairs beautifully with salty cured bacon, and it is absolutely classic with fresh eggs.
I really love the traditional idea of foraging early in the morning and making a fresh St. George's omelet on St. George's Day.
It is a beautiful seasonal tradition, and because of that dense texture we mentioned, it also works incredibly well folded into heavy cream sauces like a stroganoff or slowly stirred into a rich risotto where you really want distinct, chewy chunks of mushroom, not just a vague background flavor.
Okay, let us say I get incredibly lucky. I find a massive, pristine, several hundred-year-old ring, and I ethically harvest, say, 5 kilos of them. What do I do with the excess? Do they preserve well?
They do. The easiest method is to completely dry them out. They dehydrate exceptionally well.
Does that ruin the flavor?
No, it actually massively concentrates the umami flavor. You can dry them, store them in a glass jar, and then rehydrate them much later in the year.
So you could toss them into a heavy beef stew in the dead of winter.
Exactly. Add them to a dark winter stew to instantly bring back a bright, vivid memory of the spring.
What about pickling? You mentioned they love this in Italy.
Pickling is a huge tradition there. They call it prugnoli sott'olio, which just means preserved under oil.
How do they do it?
You briefly blanch the fresh mushrooms in a sharp white vinegar and water solution to preserve them, and then you pack them tightly into jars, completely submerged in high-quality olive oil with maybe a few peppercorns.
That sounds amazing.
Because of their natural density, that firm texture stays perfectly intact in the oil for months. They make incredible antipasto.
This has been quite a massive journey today. We literally started just looking at a weird little white mushroom sitting in the grass.
And we ended up somewhere completely different.
We ended up with a centuries-old, soil waterproofing, bacteria jamming, grass drugging moving superorganism that tastes great in an omelet.
That really is the absolute joy of doing a deep dive into biology. You casually pull on one tiny loose thread, like a faint green ring in a park, And you suddenly find an incredibly complex, ancient tapestry hiding just underground.
It genuinely completely changes how I am going to walk through the local park this spring. I am not just going to be casually looking for little white mushrooms anymore. I am going to be actively looking for the massive hidden patterns.
That is exactly what you should do. Read the landscape as you walk. Look for the sunny patches of unnaturally lush grass. Look for the distinct dead zones. Because even if the actual fruit bodies, the mushrooms, aren't popping up yet, the massive organism itself is definitely there.
Just silently waiting under the dirt.
It is always waiting right under your feet.
That is exactly the provocative thought I want to leave you, the listener, with today. When you casually step inside a fairy ring in a park, you aren't just standing on a slightly different patch of grass.
Not at all.
You are physically standing directly inside a single continuous living entity, an entity that might actually be older than the country you currently live in. It has been silently, patiently terraforming that exact specific patch of earth, inch by slow inch, since the Middle Ages.
We truly are just very temporary, fleeting guests in its ancient territory.
So this April, go outside, walk the fields, look closely for the hidden ring, carefully check the gills for that tiny Sinuate dip, smell the cap for that heavy punch of wet flour, and maybe try baking a mushroom oatmeal cookie.
For science.
Strictly for science. Thank you so much for joining us and listening to the Deep Dive today.
It has been a pleasure, as always.
See y'all next time.